what I would encourage you, okay. Okay, so before I start talking about what we're going to be covering today for the recording, let me respond to your questions about homework. The way I would suggest you do your homework is have scratch paper right there. Not the homework paper that you're going to turn in or keep in your folder. But you have your scratch paper there, you play with the problem on scratch paper, and then right then you come back over on your finished paper and you go ahead and write out the problem. And not necessarily, try not to have an example sitting there next to you similar to the problem you're working. But play with it on scratch paper, get your thinking lined out, and then sit there on your paper and write it out. I don't expect your homework to be publishable, okay? I expect it to be neat, tidy, complete, and the steps shown with some English comments and some graph sketches in there, okay? So that's what I'm looking for in that. And next week, I probably will collect an assignment maybe from you. And then I will look it over quickly and give it back to you, say, the next day. So I can give you a little feedback about what's looking good, what isn't looking good. All right?
Thank you.
Okay. So let's go ahead and continue on today. And what we want to talk about is the other trig functions. And previously, in the last session, we introduced the sine and the cosine functions, and we saw how we made a connection between the changes that occur in that unit circle as we let the angle change. And we saw how that transitions into a table of values, which we then represent as a graph. And we learned yesterday that the sine function has some symmetry. What type of symmetry does the sine function have?
Odd.
Odd function. It's odd symmetry through the origin symmetry. And we call it an odd function. And the cosine turns out to be an even function. Okay. We're going to spend a little more time on that first. And then we're going to, and we'll play with the transformations associated with those a little bit. And we'll continue to do that for the next few weeks. Very important subject of being able to squeeze and stretch and shift these things to make the use of trigonometry real to you. We want to cover the other 4 trig functions. So if we have the understanding of the sine and cosine, you're going to see that it's going to be relatively easy then to develop the actual graphs of the tangent and the cotangent function. And we'll do that in segment 2. Segment 3, we'll try to address the secant and cosecant. And then finally, we'll try to work on or offer some examples with providing transformations associated with those 4 other functions besides the sine and cosine. All right? So let's come back to the sine function first. And what you want to have in your library of functions, you folks have a whole bunch of these in your brain. You know that this one is probably x squared from algebra. You know that this one is probably, that's not a logarithm, it starts right here, square root of x. Don't forget these things, okay? We're a quick review, okay? Let me put another one up here. We have this one, x cubed. Okay, now, 2 of you have been responding. The rest of you have been quiet. I want to hear from the rest of you, okay? Very quiet class. Very attentive. That's a logarithm. I don't tell you what base because I'm not giving you anything other than what's this point here? You two be quiet. Well, that isn't at 0, and it's an x-intercept. What's the location of that on the elementary logarithm graph? Any logarithm graph? What's the coordinates? 1, 0. Don't forget that. So this is a logarithm. It could be a natural logarithm graph. It could be any base b logarithm. Okay? How about this one? Now, again, a couple of you be quiet. Horizontal asymptote, trending in this kind of way. What kind of function is it? Exponential function. Like, example? It could be bacteria growth. It could be money growing over time. Right? Okay? And so it's got some base with an exponent that is variable. That's why it's called an exponential function. It might be something like e to the x. Or, in general, some positive number for a base raised to some unknown power. Okay? If you are rusty on these, please come over to the Math Resource Center and check out the DVDs of the college algebra session on library of functions. You need to remember these. Almost every one of you are going on to calculus or other science courses, science business courses. You need to know these kind of fundamentals. Okay. There are a number of others. Here's one that shows up quite a bit. Nice V-shaped thing. It's absolute value of x. Okay? Now, that's all algebra, college algebra level type of stuff. And there's several others as well. Here we are now in this new course called trigonometry, and we just in the last session saw our first trig function as a graph looks like this. Okay? And it continues throughout the domain of real numbers, x or theta, if you want to think of them as angles. And these are the output values called the sine of x or the sine of theta. Clearly it has origin symmetry. It's an odd function. And it has a domain, we went over in the previous session, of all real numbers, or if it's degree measure, all possible angles, from infinitely large down to infinitely small angles off to the left. Okay? That should be okay based on our discussions from the previous session. We have another function that is this same shape as this, except horizontally shifted in such a way that it puts the top of this function right here on this axis. And then if it does that, then it's going to transition. It's actually going to look at something like this. And then it continues on like that. Okay, and it finishes, if it starts here on the top, on a maximum, it'll finish over here on a maximum. Okay? And this is our, what function? Cosine function of x. Again, the domain is all real numbers, and here's our x independent variable values going horizontally. Both of these functions rise and fall. They have intervals where they are increasing as they rise up as you move through the domain. All right, remember increasing functions? You did that back here in algebra. This cubic function back here is rising. It's an increasing function throughout its domain on the elementary form. The logarithm is an increasing function. This exponential, where this base is greater than 1, like e, 5 to the x, 10 to the x, and so forth. Those are increasing functions. The square root function in its elementary form is an increasing function. Okay? We also, in trigonometry, you see here, we have intervals in the domain between this top and maximum and minimum, intervals where the function is decreasing. We'll be asking you questions about that. What intervals is this particular function you might have decreasing? And you'll specify that similarly to what you did in algebra. So you see how this is connecting back to what you learned in college algebra and maybe what you forgot? Okay. So if you need to, please go back to watching the old DVDs or looking back in the earlier chapters of your book. Similarly, on the cosine function, you can see it has an interval between the maximum and the minimum where it's decreasing as well, and it has other intervals where you can see it increasing. Now in trigonometry, with these sinusoids, they have a range of values, don't they? A range of values. And the range is between what values as the bottom and the top, minimum and maximum.
-1 and 1.
-1 and 1. So the range of these things is bracketed inside an interval, including the endpoints from -1 up to 1. I like to describe that as a water level rising. As the water level rises, where does it first touch this graph? At -1. If it continues to rise, you're getting good values out of this function as the water level rises until it gets up to and includes a height of 1. And beyond that, up above, it doesn't exist. Okay. That's similar for both of these functions. Now, I tried to draw these, and I did a pretty good job. Notice that the interval for what we call the period match up. That distance gets through one cycle, doesn't it? Distance in the input, x, or theta. And similarly, down here, you've gone from a maximum to a maximum, and the trend as you move across this is you're transitioning, you're starting to fall off as you move past this point. Similarly, over here, as you move past this point, it starts to fall off. So the graph takes this much of an interval for it to finish a cycle. What's the period? We call that the period. What's the period? Is what? What's this length?
360 degrees.
360 degrees would be another way of describing it. 2 pi, and we mean that to be radian measure. Okay. Or we could even say 1 revolution, couldn't we? 1 revolution. So we're going to use that word, period, frequently in trigonometry. That's the amount, that's the minimum amount of an interval, the minimum size of an interval for which the particular function in trigonometry starts to repeat itself. Both of these functions have periods of 2 pi, or 360 degrees, or 1 revolution. Excuse me, Todd?
Can you repeat the definition of that?
Yeah, well, it's how much domain do you need to use for this thing to start to do its thing again, for it to start to repeat its behavior, is a casual way of saying it. Does that make sense? Does that make sense, Todd? Mm-hmm. How much does it take? And it's going to take 2 pi if you haven't done anything to this other than call it sine x or cosine x. It's going to take 2 pi for it to finish 1 cycle. We also can call that, as I said, 1 cycle. Okay, very, very important stuff. In trigonometry, for these things in general, I mentioned this word in the last session, if you have either a sine or cosine kind of graph, either one of these, in general, if you're talking to some engineer, an electrician, or somebody like that, or maybe a population biologist, they would say, oh, I'm modeling this information as a, what's the word I used in the previous session? Sinusoid. I'm modeling the data as a sinusoid. That word should stick in your brain. That means you're modeling something, whatever field you're studying or applying this mathematics to, you're applying a sinusoidal model, a model that behaves like this, either one of these, to whatever data you've collected. It's called a sinusoid. I think I've said this before, in listening theory, how much of what is spoken do you actually hear and retain? What percent? About 30%. About a third, roughly. You hear me repeat myself, don't you? That's for 2 reasons. One reason is to try to make you hear it enough times that it might stay in your brain. And the other reason is sometimes I forget what I've said and I say it over again. Okay? Okay. But the value of the repetition is trying to get it to stay in your head. Okay. That should be comfortable for everybody based on previous discussions. Now, in the remaining time for this short first segment, where we're sticking with sine and cosine, what I'd like to do is apply some transforms, which I spent a little time on in the last session, but it may not have become too clear. Why don't you take a second and see if you can sketch, or just a rough, quick sketch of this function. Take a moment to see if you can sketch y equals minus 4 sine x. You need to make sure you have in your head the basic sine x graph that we just went over, which is right behind me here. And then you simply apply the appropriate transformation you observe here. If you're quick, you should be done. And just draw one cycle as adequate. There it is. It's an upside down sine wave because of the negative. You're multiplying the original heights of the sine function, which would look like this. You're multiplying all of those heights by 4, and you're changing the sign of them. So if you take these heights that you see as you move across this basic sine graph dotted here, you're going to multiply them by 4. That amplifies the model. And you're taking and multiplying those values times a -1, which is going to take the positive portion and make it negative, and the negative portion will make it positive. It's an upside down sine wave amplified by 4. Pretty quick. Okay, very quick. Let's try another one. Oh, what's the period on this thing?
Still same.
Same as previously, right? There hadn't been any change in the period, has there? So the period would be 2 pi if I stick with radian measure. Okay, let's draw another one. Do another one. Let's say I have y equals minus 4 sine of 2x. Quick sketch. And I'm going to keep the same scaling here. Should be able to draw a quick sketch. I'm not expecting a publishable graph. I'm just expecting a quick sketch so that you see that behavior where the increasing, the decreasing portions, where the maximums and the minimums happen to lie, and where the period, what the period is. How many of you don't have it yet? A couple of you?
I don't.
Totally stuck or partially stuck?
Partially.
Partially stuck. How about in the back? Totally stuck or partially stuck?
No, dude, I'm just partially stuck.
Okay. You're probably feeling good about the -4.
Yeah, I got that.
Okay, good. Good.
Good.
Okay. You better be feeling good about the -4, right?
Yeah.
So we know this thing's an upside down sine wave that is amplified by 4, right? So we got that. That 2 right there is causing you some trouble. So there's several ways of presenting that. One way is the way I illustrated in the last session, is if I take this -4, which is outside the function, and move it over to the other side here, the way we would do that algebraically is by dividing both sides by -4. Dividing both sides by -4. So we could write this as y over negative 4 equals the sine of this x stuff over here, that thing with 2x in there. Now you know what this minus 4 does, don't you? Right? It makes it 4 times as tall, and it turns it upside down. So the little code I like to use, I've shown you this before, is I draw something like that. It means I'm vertically stretching it because of that 4, and I'm also at the same time turning the graph upside down. Okay? That's a linear transformation on the y variable. That's the fancy math we say. It's a linear transformation on the y variable, and you can see the structure right here, which came from this original. Now, what I showed you in the last session is the behavior inside here is regarding the input, and this is always the part that confuses people. So if you're confused by that, don't worry about it, because it's normal. Now, if you're starting to play with the x behavior, okay, the x behavior, stretching or squeezing this way, does it make sense to you that probably the mathematical behavior on y kind of structure here would be kind of similar to what you should expect to see on the x stuff, the input area here? So let's put this thing in a form that lays out just like you see here. So that 2, like I think I did the same one in the last session with you, if that 2 right there can go down underneath the x as a what? Algebraically, or with arithmetic. It goes down as a 1/2 underneath. X over 1/2. Remember invert and multiply? Oftentimes here in Trig, the early part of Trig, one of the big hurdles for people is lack of skill with fractions. If you take x divided by 1/2, you could multiply the numerator and denominator by 2, right? If I multiply the top by 2, I get 2x, and if I multiply 1/2 by 2, I get 1. So it would take me back to this. Okay? Now, look at this. Look at the pattern. You're comfortable with this minus 4, what it does. Look over here. If this behavior in y
Makes it stretch up and down, and the behavior in x maybe makes it stretch out the other way.
right on, yeah. Now, if it's 1/2, you know what 4 does.
Right.
That caused it to get stretched like a piece of saltwater taffy or rubber band, right? What do you expect the 1/2 to do? Squeeze it in like an accordion, right? You're in here messing with the x variable. And it's going to make it 1/2 as wide. So, here's your original graph with the -4 multiplier on it, right? That graph we just had previously. If we then take that thing and change this input right here to be 2x, which becomes then, thinking of it this way, then what we're going to do is we're going to take every one. Now, watch this. We're going to take all of the x readings you see, and normally you're going to grab these zeros, and you're going to grab the maximum spots and the minimum spots, and you're going to make them 1/2 as much. This is actually kind of fun once you get used to it. Makes them 1/2 as much. So instead of this being at pi, that point, that's going to become 1/2 of that, pi over 2. And that ending point on the end of the cycle at 2 pi, 1/2 of that, 1/2 of 2 pi is pi. And this minimum, instead of at pi over 2, it's going to be 1/2 of that, which is pi over 4. So you can see mathematically or graphically that that becomes then a squeezed or compressed sinusoid, And so what we do is we just draw an upside down one, and we have to be a little careful. Here's where it's going to finish its cycle, and here's where it's going to start its cycle. And since it's upside down because of the -4, it's going to take a dive, and it has to finish its cycle by the time it gets to here. So what we need then is we need to take this period here and we need to cut it into fourths, into quarters. So a quarter of pi is what we're going to use for our tick marks. So a quarter of pi is pi over 4 right here. And then we have 2 pi over 4 and 3 pi over 4. And then finally we get to pi. And so then we're going to lay on that upside down sinusoid and let it finish a cycle in this distance pi. So we drop down to a bottom, come back to a 0, go up to a crest, and drop to a 0. And I just used the word for the first time called a crest, just like the crest of a wave. And what would you expect on a wave if you're out in the ocean on a surfboard or out there in your life vest going up and down with a wave action? You'd be down in the trough.
I know about some surfing.
What was that?
I said I know about some surfing.
Okay, good. That's a good thing to know about. So we cite, and we can call that a minimum, as I did previously. We can call that a maximum. But in sinusoids, oftentimes we speak of troughs and crest. What's the domain of this function? Domain. All real numbers. Domain is still all real numbers. And what's the range?
-4 to 4.
Right on, -4 to 4. Whoops, includes the endpoints, square brackets on that interval. Any questions? Yes?
If the same y equals -4 sine of 2x, if that 2 is a number less than 1, then are you stretching it?
Well, let's find out.
Yeah, like if it was 1/2 x, it'd just go the other way and double instead of the half.
Yeah, let's do one. Let's do a cosine, and then we'll wrap up this segment. Okay? Sketch this one. Now I'm going to make it can be written as x over 3, or it can be written as 1/3 of x. Sketch that. I want you to observe the following. Here's what I like to call the transform form over here. The transform form. You can see here, this is the y stuff, which has been stretched by a magnitude multiple of 100. And over here, paralleling it, is the stretching horizontally by a factor of 3. So what I would draw is I'd simply start drawing a nice old cosine wave, real simple. Right? Nice and smooth. And instead of ending its cycle at 2 pi, the period is going to be 3 times 2 pi, or 6 pi, for the period. So you'd label this as 6 pi. You'd label your crest at 100 instead of at 1, and your trough down at -100. It's that simple. You just draw a cosine and label it, indicating your scaling.
So you only have to label the end of your period. You don't need to make all the marks in between, unless they ask you
Very
to.
good question. I would, okay? I would label a few other marks. Now, I mentioned earlier, how frequently do we want to cut up our domain? In quarters. So what we typically will do in trigonometry, keep this in your head, in trigonometry we will figure out the period of the function, and then we'll typically cut it in a quarter. And I oftentimes will write that down. 1/4 of my period, I write it down so I can clearly see it in my notes, is 6 pi over 4, which is then, reduce that, 3 pi over 2. Okay, so then I can come back on my graph paper and I can mark this point at 3 pi over 2 and this point at 2 of those, which would be 3 pi, which you should expect to be half of 6 pi, right? And then if you have 3 of those, look at that, 3 of these quarters right here. 3 of these is 9 pi over 2. See how easy it is if you do it this particular way? Otherwise, sometimes these fractional portions here are going to be confusing. Okay. That's a big part of this course, is being able to do these kind of things. And one closing remark before we end this segment. Is checking to see if your sketch is accurate. So let's say this is our function, we call it f of x. And I drew this sketch by hand, and I don't have my calculator. How can I spot check this to see if this sketch matches, ties in with that equation? Throw in a value of x. So I look at my picture, and what if I came in here, say, at 3 pi over 2? I should hit a 0, shouldn't I? Okay, so let's try it. F of 3 pi over 2, investigating this point right here, let's see what happens. I have 100 cosine of 1/3 of 3 pi over 2, dropping in there. Clean that up. And now go back to your unit circle. Think of your unit circle, folks.
Yeah.
When you're at 90 degrees, this is why I was hammering you for a week about learning that unit circle. You go back to 90 degrees now with your unit circle thinking. Let's bring the camera, where are we? There we go, okay. You bring it up to 90 degrees, and what's that cosine reading? Is the x reading, right?
0.
The x reading. The x reading is 0, right? Cosine comes down from 1 towards 0. At 90 degrees, that's 0. And this thing turns, that term right there turns to 0, and you get 0, which matches this 0 on the function. So it's a quick way to spot check to see if you got it laid out properly. Spot check with at least one point, maybe another point or two. But it takes you right back to ground, to the original thinking that we started the course with. When you're on your unit circle at 90 degrees at pi over 2 here, your cosine reading there is 0. 0 and a 1. 1 is the sign, but we're doing the cosine there. Okay, let's end this first segment, and then we'll go on to these other 4 trig functions here in the next segment.